Thank you for the introduction, and well, still good morning, ladies and gentlemen, and welcome to the presentation You Can Run But You Can't Hide, a holistic security analysis of Google Fuchsia's and Google gVisor's network stack. My co-authors are Inon Kaplan and Ron Evan, and I'm Amit Klein from the Hebrew University of Jerusalem, School of Computer Science and Engineering. So a bit of background, what are these Google Fuchsia and Google gVisor products? Google Fuchsia is a general-purpose operating system designed to power a diverse ecosystem of hardware and software, Google's own words. It targets the mobile and tablet and IoT devices, and it's already deployed to millions of Google Nest Hub devices. It's conjectured by many analysts to eventually, maybe, hopefully, replace Android as the mobile operating system of choice. Hence, the presentation is under the Android security. And interestingly enough, Fuchsia's TCP/IP stack, also called NetStack, is actually a copy of gVisor's network stack, and gVisor is an application kernel for containers. It's used in multiple Google Cloud offerings, such as App Engine, Cloud Functions, Cloud Machine Learning Engine, Cloud Run, and last but not least, Google Kubernetes Engine, GKE. So our approach is a holistic security analysis where we analyze the entire Fuchsia and gVisor TCP/IP stack en masse. We focus on the high entropy protocol header fields. These are the usual suspects, starting with the IPv4 and IPv6 ID, where we find some issues. In the IPv6 flow label, we couldn't find anything for the prosaic reason that it's always 0. And then we moved on to UDP source port, TCP source port, TCP timestamp, and TCP initial sequence number, where in each we found some security issues. And then we went on to combine those somewhat weak security vulnerabilities in separate network protocol headers and separate network layers into some powerful attacks. And this is the map on the diagram of the attacks we found. We found 6 vulnerabilities, and we were able to combine them. For example, in the TCP IPv4 case, we combined 4 vulnerabilities and using 4 TCP SYN packets to find the network stack PRNG seed, which is 31 bits. Alternatively, we could use the IPv6 with 2 packets only, and combining only 3 vulnerabilities to find the same seed. Or we could use UDP with a rainbow table attack and 0 packets. You may wonder how come we could pull this trick. Well, we can force the operating system and the browser to allocate us UDP source ports using WebRTC without actually sending any network packet. So with 0 packets, we could again find the same seed. And using that seed, we can find various interesting we can leak some interesting information and predict some interesting protocol header fields. Particularly using the IPv4 internal address and another vulnerability, the vulnerability of the IP ID, and using a hash collision attack with 250 packets, we can find another key, the IPv4 ID hash key, which is an additional 32 bits, and it can allow us to predict further fields and to leak further information. Finally, using the PRNG advancing weakness, with UDP, again using the 0 packets trick, we can predict the PRNG and predict UDP ports, future UDP ports. I'm going to focus today on the TCP IPv6 attack, which combines the small PRNG seed vulnerability, the TCP timestamp weak hash, and the TCP source port global counter, using 2 TCP IP SYN packets to find the network stack PRNG seed. That's again 31 bits. So in order to do that, let's first understand how TCP timestamp is generated. You can see the equation here. It's a hash of the source IP concatenated with the destination IP with a secret key plus a time in milliseconds. And this hash function is simplified here for the ease of discussion. Jenkins 1 at a time hash, where X is an array of bytes and state is a 32-bit internal state. And the key that I mentioned is generated at kernel startup. It's one of the TCP secret keys, and it is generated deterministically from the 31-bit seed, which makes it valid from system startup to system shutdown. And the hash function itself is weak because it has only a small internal state, only 32 bits. And if we know the hash of X and state, and we know X, then we can easily find what the initial state is. We call this process peeling. If we have a hash of X concatenated with Y, it's the same as the hash of Y, with the state of being the hash of X and the original state. We call this the chaining rule. So by the chaining rule, we can see that the timestamp is a hash of IP, the destination IP address with a quantity called J plus the time in milliseconds. Now, the first order of the day is to find J, and we do that by forcing the Fuchsia device using malicious JavaScript in the browser, maybe forcing the user to navigate to attacker site. And using the malicious JavaScript, or e.g. WebRTC, we can force the browser to send us 2 TCP SYN packets rapidly. And you can see the timestamp calculation on the right-hand side. Those 2 packets go to 2 different attacker IP addresses. And by subtracting and rearranging the equations on the right, we get to this lovely equation where at the left-hand side, everything is known to the attacker. The attacker can observe the timestamps at the attacker's IP addresses. And where delta t is small, we cap it from above by 20 milliseconds, so that leaves it only with 20 possible values. And at the right-hand side, everything is known except j. So we have something known at the left-hand side equals a function of known parameters at the right-hand side up to an unknown quantity j of 32 bits. And this function is computable in offline. So we invert it into another function q that we calculate in offline. And then we find the j candidate by feeding q with the right-hand side, which is known. And we get 20 candidates of j. And from that, we find seed easily. We start with peeling from J with the known source IP address to find key. And since key is generated deterministically from a 31-bit seed at system startup, we can invert this generation function into a multifunction W and feed it with the key to find the seed candidates. So we have 20 seed candidates. And from the seed, we generate the other TCP secrets, the 3 TCP secrets. One of them is the TCP source port secret, key prime. And we use that to verify with the 2 TCP source ports that are generated by Fuchsia for the TCP SYN packets. And we can subtract, compare, and verify that we have matching left-hand side and right-hand side. And the net result is that only a single correct seed would survive this verification. And what do we do with this seed once we found it? Here's a nice use case, web-based device tracking, or as we call it, coast-side tracking, where we have a mobile Fuchsia device. It connects to the first website, and the website generates a device ID for it. On a second day, maybe on a second network, maybe from a different browser, it connects to a second website, and it still generates the same ID for it. And on the third day, maybe from an incognito mode, it connects to a third website and it still generates the same device ID, even though the 3 websites do not share any common infrastructure, no common domain, no common IP addresses, nothing. And how do we do this magic? Simply use seed, those 31 bits, as our device ID. Those 31 bits are unique up to the birthday paradox. And the nice thing about them is that they're stable across sites, across browsers, across networks, across privacy mode, and they only get regenerated on boot. So to summarize the TCP IPv6 attack, we obtained a PRNG seed, which is a stable device ID until next reboot. That's 31 bits device ID. And we can also derive the TCP secrets, the one used for TCP timestamp secret, the one used for TCP source port secret, and the TCP ISN secret, which allow us to predict those TCP headers in the future. We also get the seed, so we can predict PRNG values in the future, hence UDP source port prediction. And we get the TCP outbound connection counter and the machine time since boot, which is a nice information leakage. And we perforate in runtime of few opcodes, just 20 table lookups in Q, 20 table lookups in W. That's really negligible. And modest RAM, only 56 gigabytes. Now, here's a nice thing. If we have a dual stack, so both IPv4 and IPv6 on the same device, we can use another TCP IPv4 SYN packet to obtain the IPv4 internal address. And then if you recall the diagram I showed earlier, we can use the IPv4 address to get another 32 bits of ID. We conducted some experiments on 4 Google Fuchsia devices and 7 different networks and got excellent results. And our root causes are weak. As you can see here, we circled out 4 root causes: weak hash function, which can be fixed by moving to a cryptographic hash; a weak PRNG, which can be fixed by moving to a cryptographic PRNG; a global counter, which can be mended by moving to a fully randomized TCP source port; and a weak generation ID scheme, which can be mended by fully randomized IP ID. And as you can see, Google went on and fixed Google Fuchsia and gVisor according to our recommendations. So to summarize, we see it is a demonstration of our holistic approach where the whole is bigger than its parts. We combine some smaller vulnerabilities and separate functionalities and components and across network layers and use them in concert to mount some powerful attacks. We see that clean slate design, which is what we have in the gVisor TCP stack, does not guarantee secure code base. The design may be clean and good architecturally, but security is sometimes in the details, and it's always important to learn from other people's mistakes. And it's another example of device tracking via network stack objects, which is a concept we explored in our recent papers, where we find vulnerable protocol header field. We extract the key or the seed that is used by the kernel to generate it, and this key or this seed is the device ID. Thanks for having me. If there are any questions.
Questions?
Hi, Amit. Thank you. Excellent.
Hey.
As expected. Amit, did you try to find if there's any abuse of this by any tracking of users?
I'm sorry?
Oh, well, this system is not really deployed, but of your previous work, did you try to identify any actual tracking of users using this? Not this one again, the previous work.
Oh, my previous papers?
Yeah.
I'm not familiar with in the wild attempts to use those papers, but I was approached by someone asking for some kind of a copyright assignment or something like that, so that he or she can use one of my earlier techniques. Yes.
To use it to track people.
Yes.
Okay. I was of course asking about if there's been any kind of attempt to check if people are using these sort of techniques.
Oh, I see. I really don't know.
Okay, thank you.
I have another quick question. So about 2 years ago, or maybe even earlier, I wanted to look at the Fuchsia's implementation as well, because I've been looking at TCP, IP, like UDP side channels myself, and my impression is that Google's Fuchsia's networking stack is very primitive. It didn't implement a lot of the advanced features. Like there was no challenge ACK at the time I checked, for example. I wonder if that's the reason why there are so many issues.
I think what you're first. I agree to what you say. I think it's ongoing work. Their TCP stack implementation. It's definitely not as sophisticated as Linux. And I think part of it is the second bullet in my last slide that says that they were not learning from other kernels implementations or mistakes and things like that. So that I think they wanted to go through it in a clean slate manner without actually taking a lot of influence from from existing implementations, and results were, well, you could see the results.
All right, I guess let's thank the speaker again.